Alright, welcome to page 4 of section 7.3, and here you're going to have the second translation theorem. So, if cap f of s is equal to the Laplace transform of f of t and a is greater than 0, then the Laplace transform of f of t minus a times the unit step function of t minus a is equal to just e to the negative as times cap f of s. So the proof of this is we're going to go ahead and substitute in f of t minus a times cursive u t minus a into our Laplace transformation, so our integral times e to negative st. And because this is a step function, because this is the unit step function, this is going to be a piecewise defined function from 0 to a and from a to infinity. So we're going to break up our integral from 0 to a of our function plus a to infinity of the inside of the integral. Now, one thing to notice about this part is that, remember, this function right here is 0 until we approach a. So if I'm from 0 to a, this part is just going to give me 0. So this goes away. So really, we're only doing the integral from a to infinity of e to the st. And now, once we reach a, don't forget that this unit step function, instead of it being 0 now, this is going to be 1. And so we're really just dealing with e to the negative st times f of t minus a. And so that's the integral that we're working with. Now, because we have a variable with some constant what we don't know, then what we're going to do is we're going to use kind of u substitution, but instead of using u, I'm going to use v. So v is t minus a, and dv, the derivative of this is just going to be dt, the derivative of t and a, where a is a constant and t is my variable. So the derivative of that's just dt. Now when we substitute in, e to the negative st is really, if v is equal to t minus a, then t is equal to v plus a. So we're going to substitute that in for our t. And then this t minus a is just f of v d of v. And now what we're going to do is we're going to pull out we could distribute this negative s into our exponent and get negative sv minus sa. Now, what you need to remember is that s and a are both constants, so I can pull out that e to negative as. And the only thing that's going to be left inside is e to negative sv times f of v dv. And then if we do the integration of this from a to, make sure those are fixed, from a to infinity, then what we're going to get is back to our, back to the original e to negative st, but instead of t, it's now v. So this, when we take the integration, it's just going to give us cap f of s. And so our function of s times e to the negative as, because we pulled that out. And so that's why this works. So anytime we're doing Laplace transform of a function of t minus a times the unit step function of t minus a, it's just e to the negative as times cap f of s. So what we want to do is we want to try to identify that, t minus a. So right off the bat, we look at this, we want to do a Laplace transform of the unit step function of t minus a. Notice there's no f of t. Well, the reason why so when we look at the Laplace transform of this, we just get e to the negative as times 1 over s. Now, why is that? Well, whenever we're doing the Laplace transform of the unit step function, we're always going to have to multiply that by e to the negative as. So what we have to realize is, well, what was our f of t? Well, if our f of t is not shown here, our f of t should be 1. And because f of t is equal to 1, then f of t minus a is also going to be 1. So if I do the Laplace transform of just, a constant, or 1, that's just going to give me 1 over s. And so the Laplace transform of just 1 is 1 over s. So I'm multiplying 1 over s times e to the negative as. which is going to give me that value. So, for example 9, it just says write in terms of unit step functions. So I'm going to write this function in terms of a unit step function. So we start off at 0, so I don't put anything there. I don't say 0 plus. I could put 0 plus, but I'm not going to because I don't need to. And then we're not 1 until we reach t minus 1. So until t reaches 1. And so when this reaches 1, this value is 1. We're not, this value is 1 as well once we reach 2. This value is 1 once we reach 3. This value is 1 once we reach 4. And so then this is 1. And then we get to 2 once t is 2. We get to 3 once t is 3. And we get to 4 once t is 4 because it's 1 plus 1 plus 1 plus 1. But they don't start until the t reaches 1, 2, 3, and 4. Alright, so example 10. We have the Laplace transform of e to the 2 minus t times the unit step function of t minus 2. And so what I want to do is I want to figure out a way. I want to have f of t minus a times the unit step function of t minus a. So I want to have the function and the unit step function to both be in the form of t minus a. And right now I don't have that. I have 2 minus c and t minus 2. So I want them to both be in t minus 2. So in order to do that, I'm going to change up the way 2 minus t looks. Instead of having 2 minus t, I'm going to have t minus 2, but pull out a negative. And so now I have both my function and my unit step function in terms of t minus 2. That means that my a is 2. So then that means that the outside is going to be e to the negative as. So again, the outside is e to the negative as. So in this case, it's e to the negative 2s times the Laplace transform of e to the negative t. Because I'm now just dealing with my function. Instead of t minus a, I'm going to make it just t. So it's just e to the negative t. And if I remember back some notes ago, the Laplace transform of e to the negative t is just 1 over s plus 1. And then again, times the e to the negative 2s on the outside. So it's just e to the negative 2s over s plus 1. Finally, for example 11, we're going to do the Laplace transform of 3t plus 1 times the unit step function t minus 1. Because I have a unit step function with t minus 1, I want both my function and my unit step function to have the same t minus a. So I need a t minus 1 on both. So in order to get a t minus 1 over here, and I have that 3, and since that I have a 3 here, what I want is have a minus 3. So now if I have a 3t minus 3, I can pull out a 3 and get the t minus 1. But there's a problem. I have this 4. I have to incorporate this 4 because negative 3 plus 4 gives me back that positive 1. So I keep the same value for this function. So this is the way we break it up. And I can do this because, again, because the Laplace transformation is linear, then I can break this up to 3t minus 3 times the unit step function t minus 1 plus the Laplace transform of 4. So I broke up the 3t minus 3 to be the 3 times t minus 1, and then the 4 times that unit step function. And now I'm going to pull the 4 out, I'm going to pull the 3 out, and then I have t minus 1 times the unit step function t minus 1 plus 4, and then again I have 1 times the Laplace transform of the unit step function t minus 1. So on the left, when I look at this, I can get rid of my unit step function because I'm pulling out my e to the negative s. The reason why it's e to the negative s is because my a is 1. And so 3 times e to the negative s Laplace transform of t plus 4 times e to the negative s Laplace transform of 1. T because that's t minus 1, and then 1 because the function is just 1. Laplace transform of t is 1 over s squared, Laplace transform of 1 is 1 over s, multiplied by e to the negative s, and 3e to the negative s, and I get 3 to the negative s divided by s squared, plus 4e to the negative s divided by s.